So let's finish up with section 1.2. Okay, we left off with theorem 1.2.5, a very useful result for establishing that a set of elements from a group actually is a subgroup. Next, we'll make the claim that if G is a group and H sub I, where the subscript I comes from some indexing set capital I, if this is a non-empty set of subgroups of G, then the intersection of all those subgroups is itself a subgroup of G. Now, a little comment about this. How many H sub i's are there? Well, there's one for every index in the indexing set, so it becomes an issue of what's the cardinality of the indexing set. So we're not just taking an intersection of necessarily a finite collection of subgroups of group G. The indexing set I could be infinite. It might even be uncountably infinite. So no constraints on the cardinality of I. You might have seen something along these lines where you took an intersection of two subgroups of a given group in your senior level algebra class and shown the intersection of two subgroups of a given group is again a subgroup. And by induction, the intersection of any finite number of subgroups is again a subgroup. But here we don't have that finiteness, so an induction proof wouldn't work here. Here we'd have to do something slightly more sophisticated. The proof is not very complicated. It's left as an exercise. But intersections of subgroups are subgroups, arbitrary intersections of subgroups are subgroups. Now, none of this would make sense, and I couldn't just grab a group over here and a group over there and take the intersections of them. This all has to be going on in the setting of some larger group, which will be the case probably in the next couple of sections when we look at these results of combining groups in various ways. So this is all happening inside some big group G, and we're looking at subgroups of group G and taking intersections. Next definition, related to this previous idea, is to take a group G, everything here again is happening inside group G, and let X be a subset of group G. So it's simply a set of elements of G. Consider H sub I to be the set of all subgroups of G which contain set X. So here we've got H sub I as subgroups, and these subgroups include all of them, this subset X of elements of group G. Then, definition, we're saying take all such H sub I, intersect them, and that is by definition the subgroup of G generated by that set of elements X from group G, denoted with angle brackets. So given any set of elements, we'll find all subgroups of group G that contain that set of elements and intersect all of them. There is some group, a subgroup of G containing that set of elements, right? This isn't an empty collection, right? Group G itself necessarily is a group that contains a set of elements, so there is something to intersect there. So intersect all those subgroups, that's what we mean by the group generated by a set of elements. We'll spend a moderate amount of time looking at generators of groups. We haven't formally defined this yet. We will in the next definition, but you're probably familiar with a case when we look at a group generated by a single element. It's called a cyclic group. You explored these in senior level algebra. Likely you know if we have a cyclic group, a group generated by a single element, then that group is either isomorphic to Zn if it's a finite group of order n, or it's isomorphic to Z itself, the integers, if it's an infinite group. More formally, given a group G, the elements X, collection of elements of group elements, are called generators of the subgroup generated by that. So we're just giving a name to the individual elements. They're called generators of the subgroup. If G is generated by a finite number of elements, it's called finitely generated. If G is generated by a single element, it's called cyclic. And just to keep things clean, we made a little shift here, dropping the set brackets down here. Technically, groups are generated by sets of elements. So I need set brackets as given here let's be a touch informal, which is standard notation, and let's drop the set brackets when we actually list elements of the set. So finitely generated groups and cyclic groups. Theorem 1.28 tells us what the elements of a group generated by a set of elements looks like. What the elements of group G, when G is generated by set X, what those elements look like. The statement is, if G is a group and X is a non-empty subset of G, then the subgroup generated by that set of elements consists of all finite products. Infinite products don't make any sense unless we can do something with limits, and a group just doesn't have enough structure to do that. Group generated by X consists of all finite products, a sub 1 to the n sub 1 power, a sub 2 to the n sub 2 power, up through a sub t to the n sub t power. The a sub I are chosen as set elements, the n sub I are integers, and t is some positive integer itself. We've mentioned we have the interpretation when this exponent is when the exponent, say n sub 1, is a positive integer, it represents repeated applications of the binary operation, a sub 1 squared, a sub 1 times a sub 1, and so forth. When it's a negative integer, it represents repeated binary operations of the inverse. A sub 1 to the negative 2 power, if you will, is a sub 1 inverse times a sub 1 inverse, and so forth. And when that exponent is 0, it represents the identity of the group. So this claims that we know what the elements of group G looks like. I mean, this doesn't give us a real tangible grasp if set X happens to be large. Nobody said anything here about set X being finite, it just said it's non-empty. So could be a large set, but a set of elements of group G. The elements of group G, they look like this. In particular, if set X does consist just of a single element, then we're simply getting powers of that element. The group subgroup of G generated by element A, that cyclic group is simply a to the n, where n is an integer. All possible powers, if you will, of element A. Let's look at a proof of that. Okay, so we're establishing that the group generated by the elements of set X are of this form. Okay, well, first let H be the collection of all products of that form. This makes sense. Again, everything's happening in this big umbrella of group G. So we can take these elements of G and take products and powers as we wish. Now let X be an element of set X. We can conclude that X is a subset of H. Just to illustrate the notation here, we take T equals to 1. So we'll have a product. We're taking a product of different elements. You might want to think of it as, if we don't have commutativity, that's not the best way to think of it. But we're taking a product of simply one thing. So we're taking a sub 1 to sub power. Take a sub 1 to be X itself, the element of set X, capital X, and let the exponent be 1. Then we get X to the 1 power. Must be an element of this thing H. X was an arbitrary element of set capital X. So we get set capital X as a subset of H. First off, H is a subset of G. It's a collection of group elements. It's quote unquote clearly closed under the binary operation. If I take a product of a bunch of powers of the elements in this collection, then I get another thing of this form. Again, I may not have commutativity. If I do, we can probably draw some special conclusions. We will shortly. But if I take a product of two things of this form, I get something else of this form. The t parameter would change, but it can be any natural number. So we've got closure under the binary operation. So first off, H is a semigroup. We do have the closure that we need, and associativity is inherited from above the big umbrella group G in which all of this is happening. Now, for any X, an element of set capital X, with t equals 1, the a sub 1, so I'm looking at these kind of products, the a sub 1 equal to x itself and the exponent on that equal to 0. We get x to the 0. The very meaning of that symbol is the identity. So we get that the identity then is an H including all products of this form. So in particular, it includes the product for t equals 1, a sub 1 equals x, and n sub 1 equals 0. So we get the identity in H. It's a semigroup with an identity, that is, it's a monoid. Only thing we need to worry about now is inverses to establish that it's a group. And if we take any element of H, something of this form, then if you'll consider a sub t to the negative n sub t, a sub t minus 1 to the negative n sub t minus 1, up through a sub 1 to the negative 1. So we've taken these elements, written them down in the opposite order, and inserted a negative sign on the exponent, if you will. And that's an inverse of this element here. It's something else in an H because it's of the form of the elements of H. I multiply these two things together, and indeed we get the identity, whether I multiply first this one and then that one or the other way around. Of course, we get the identity back out. So H is a monoid with inverses, that is its group. So H is a subgroup of G, it contains X. So what we've shown then is the group generated by the elements in X then must be a subgroup of H. Remember, this is defined as an intersection of all subgroups of G containing the elements in X. This H is a particular subgroup of G. We proved it's a subgroup, which contains X. We proved it contains X right here. So if this is the intersection of all such subgroups, then this particular subgroup must contain the group generated by X. So it's a little more complicated than it might look on the surface, but that's the argument there. So we're trying to show really that the group generated by X actually equals this thing X. We've shown the group generated by X is a subgroup of H. We're going to kind of reverse this subgroup relationship, and then we'll draw a conclusion of equality. And that's what we're trying to show. Okay, so let H sub I be a subgroup of G containing X. Then this particular element of H here, we know to be an element of X. And so since H sub I is a subgroup of G containing X, H sub I contains all of these elements of X here. H sub I is a group, so we can take powers of those elements inside the H sub I group. We can multiply those things together and within H sub I, it being a group itself. And so we get that this thing here, A1 to the N1 through A sub T to the N sub T, that's in H sub I. We started by choosing an element of this group H. We showed it's an element of H sub I, where H sub I is any subgroup of G which contains the elements X. So everything in H, arbitrary element of H, is in H sub I. In other words, H is a subgroup of H sub I. And this is valid for all H sub I subgroups of G containing X. So when we intersect all of them up, we also get that H is a subgroup of the intersection of all of these H sub I's. H is a subgroup of the intersection of the H sub I's, but wait, that was by definition, that was the group generated by the set of elements in X. So we've got equality here by the definition of how the group generated by the elements in set X is defined. And now we've got H as a subgroup of this particular group. Previously, we had this particular group was a subgroup of H. So it must be that we get equality here. And H equals the subgroup generated by set X, and that was the claim. We wanted to show the group generated by set X consisted of all elements of this particular form. Okay, back to the notes. Another little idea on generating groups. Again, everything's happening in a big umbrella group G. So the following conversation all happens within group G. If I grab one group over here and one group over there, maybe I can't take binary operations of elements from different groups. We can here because all these things are elements of this umbrella group, as I call it, G. So again, let H sub I be a set of subgroups of group G. Here we want to talk about the group generated by the union of those. The subgroup generated by the union of these H sub i's is called a group generated by the groups H sub I. You know, I can take any set of elements and get a subgroup of G generated by those elements. We even know from the previous result what those elements look like. Here we're taking the set to be the union of those H sub i's. So this highlighted thing plays the role of set X, if you like, not necessarily a group itself, but there's a group that contains that union, the group generated by that collection of subgroups H sub I. If H and K are subgroups of G, then the subgroup generated by just two subgroups, denoted here, it's called the join of H and K. So unclear as why they would have this different notation, but if we have multiplicative groups, the join of H and K is indicated with a little v. If we have additive groups in the additive notation, the group generated by H and K, subgroup of group G generated by H and K, is denoted with an addition sign, H plus K. So can you tell me what the elements look like? Yeah, pretty much. Going to look something like this, where what we'd have going on here is the A sub i's are elements, say, either of H or of K. If I go through and try to describe what the elements of this join looks like. So we'd have powers of either H or K multiplied together, a finite number of them. Well, it gets a little bit more simple than that if we have an abelian group. We could collect all the elements of H together and all the elements of K together. If G is an abelian group, H is a subgroup of G, K is a subgroup of G as well, then the join, H join K, is simply all H times K, where H is in group capital H and lowercase k is in group capital K, as is to be shown in exercise 1.2.17. It'll follow simply from what we have up here. You got the commutativity. I know without the commutativity, I get elements that look something like this, where the A sub i's are either from H or K. Well, I can, with commutativity, get all the elements of H together and combine them into a single term, and all the elements of K together and combine them into a single term. That's the argument, and that's exactly what we're claiming down here. So that takes care of section 1.2. So have a nice day. Next up, I think, is cyclic groups, and we'll tackle that in section 1.3. Bye-bye.